Hello, ladies and gentlemen. My name is Konstantin Prasolov, and I'm reading the text of this lecture on behalf of Professor Sharkeev Yurii Petrovich. The title of the presentation is Features of the Structure of the Alloy Titanium Niobium in Ultrafine Grained State in a Gigacycle Fatigue. Let me thank Professor Francesca Iacovello and Professor Oleg Naimark and the organizing committee of the 27th International Conference on Fracture and Structural Integrity for my opportunity provided to take part in the conference with oral presentation. There are two main problems. In our work, we try to focus on two main problems. In what way we could improve the mechanical properties of bayonet titanium niobium alloy for medical application, and in what way we could test the titanium niobium samples in a gigacycle fatigue test during the short time interval, 1 to 3 days. We proposed the following solutions. The mechanical properties of the alloy can be improved by extensive milling of the alloy grain structure up to an ultrafine grain state using the severe plastic deformation techniques. The resonant testing machine with loading frequency of 20 kHz can be used for the fatigue testing of biomaterials, achieving the fatigue life of 10 power 9 and more cycles in a short time period, up to 1 to 3 days. The periodic table of elements is presented here, with binary metals highlighted by red circles. There are 7 such metals. 5 of these elements possess an excited passive thin film that grant them bayonet properties: titanium, zirconium, niobium, hafnium, and tantalum. These elements and their alloys serve as construction materials for medical implants. Additionally, it is important to mention resorbable magnesium and some of its alloys, which are also utilized in medical applications. The bayonet metals, commercially pure titanium, titanium niobium alloy, and zirconium niobium alloy, as well as resorbable magnesium calcium alloy, are the research objects in our laboratory of physics of non-structured biocomposites. The titanium niobium alloy is an exceptional bioinert material for medical implants due to its biocompatibility, high corrosion resistance, and low elastic modulus, which is comparable to that of bone tissue. However, this alloy possesses one drawback: insufficient mechanical strength. The titanium niobium alloy exhibits an elastic modulus within the range of 50 to 60 gigapascals. Alloys of this composition are utilized in medical application as materials for medical implants. The yield strength of the alloy in its normal coarse grained state is 400 megapascal, a value that is inadequate for implant use. To enhance the alloy's mechanical properties, severe plastic deformation methods are employed to significantly refine the grain structure. By employing the methods of severe plastic deformation, non-structured and/or ultrafine grain state can be formed in metals and alloys. This results in bulk materials with specific microstructures are and considerably improved mechanical properties such as yield and strength limits, hardness and microhardness, endurance limits, and cyclic durability. We employ a combined method of severe plastic deformation consisting of ABC pressing followed by multi-pass rolling to create an ultrafine grain state in titanium niobium alloy billets. ABC pressing involves one or three pressing steps at a constant temperature. As the process transitions from one pressing step to another, the sample temperature is gradually decreased by 50 centigrades within the 500 to 400 centigrades range. After each pressing, the sample billet is rotated 90 degrees about its longitudinal axis, perpendicular to the previous pressing axis. The use of a press mold creates a space-limited deformation conditions, facilitating effective grain refinement within minimal steps. The microstructure of sample is presented in an ultrafine grain state in comparison to the coarse grain state of the titanium niobium alloy. The sample microstructure was analyzed using transmission electron microscopy with structural element size measured from the TEM dark field images. Rolling during the second stage results in a homogeneous ultrafine grain state throughout the volume with an average structural elements size of 0.28 millimeters. Alloy beads with this microstructure exhibit low ductility under tension, not exceeding 2 to 3%. Annealing at temperature of 350 centigrades increased plasticity up to 5.5% while maintaining the ultrafine grain state. The mechanical properties of titanium niobium in the ultrafine grain state compared to its initial state are presented in the table. It is evident that titanium niobium alloy in its ultrafine grain state exhibits an excellent level of mechanical properties including yield strength, ultimate strength, and microhardness. Additionally, it demonstrates satisfactory values of plasticity and elastic modulus comparable to that of bone tissue, not exceeding 40 gigapascals. The service life of an implant is expected to be at least 15 years or more, considering an individual takes 120 steps per minute. We can calculate the total steps as follows, which results in 1 million 1 million steps. Due to this, medical requirements mandate that implants under cyclic loading have a working life of at least 10 to power 9 cycles. Consequently, an ultrasound machine for fatigue testing of biomaterials used in implants is necessary with the testing period falling within a range of 2 to 6 days. A resonant type testing machine, the Shimadzu USF 2000, was utilized in our studies by the scientific group led by Professor Oleg Naimark in Perm. The loading frequency was set to 20 kHz. The machine's general appearance on the left and schematic representation on the right can be seen, along with the sample used for testing. The gigacycle test results for the titanium niobium alloy sample are presented below. In the coarse grain state, the sample fatigue after 10 to power 7 cycles at a loading amplitude of 230 megapascals are presented. However, the samples in the ultrafine grain state did not fail after 10 to power 7 cycles, even at a higher loading amplitude of 300 megapascals. The fatigue limit of titanium niobium alloy specimen in ultrafine grain state, based on 10 to power 7 to power 6 cycles, was 380 megapascals. This exceeds the fatigue limit of 280 megapascals in the coarse grain state by 1.4 times. For ultrafine grain specimens based on 10 power 9 cycles, the fatigue limit was 295 megapascals, whereas in the coarse grain state it was 195 megapascals, a 1.5 times higher value. Consequently, the ultrafine grain structure in the alloy contributes to a significant increase in the fatigue limit compared to the coarse grain state. The microstructure near the failure surface comprised of large aqueous grains with an average size of 42 micrometers, similar to the initial state, which had an average size of 44 micrometers. In the coarse grain state, titanium niobium alloy and non-oriented dislocation substructure is observed. A notable feature of the microstructure after the fracture of the alloy in the coarse grain state is a significant increase in dislocation density and the development of a dislocation structure within the beta phase matrix grains. Additionally, ellipsoidal phase particles are presented inside the beta phase grains. The microstructure of the ultrafine grain titanium niobium alloy is depicted in Figure A. Severe plastic deformation results in grain refinement, with the main structural elements being grains, subgrains, and fragments. TEM images display beta phase and alpha phase subgrains, as well as phase particles within the bulk of beta phase grains. Upon examining the selected area diffraction pattern, reflex groups from 3 phases were identified. The average size of the structural elements for the phases in the ultrafine grain were as following presented in the slide. In the ultrafine grain alloy, a misorientated fragmented structure is formed. The average size of the structural elements of the beta phase are gigacycle testing was 0.2 micrometers. The microstructure is characterized by a high density of dislocations, which form a misoriented fragmented structure. Following failure, a fragmentation of the microstructure and slight refinement of the structural elements of the main phase are observed. Within the microstructure, alpha phase grains are presented in the boundaries and junctures of the beta phase matrix subgrains, as well as omega phase particle precipitation site beta phase grains. In the ultrafine grained alloy, the grain size is too small for the formation of intragranular dislocation structures. Consequently, grain boundaries play a significant role in dislocation annihilation during gigacycle tests. Here are the main results of the work. The application of severe plastic deformation comprising multi-step pressing and multi-pass rolling in grooved rolls enabled the formation of an ultra-fine grain state in the titanium niobium alloy. This resulted in a significant increase in mechanical properties while maintaining the elastic modulus and moderately reducing ultimate plasticity. Furthermore, the titanium niobium alloy in the ultrafine grain state exhibited superior fatigue properties under gigacycle loading. The ultrafine grain structure in the titanium niobium alloy is stable during gigacycle loading and ensure a service life up to 10 to power 9 cycles or more with enhanced fatigue strength. Second, unlike samples of alloys with a coarse-grained structure, where dislocation networks and cell form after gigacyclic test, the microstructure of samples in an ultrafine grain state remains largely unchanged during testing, although a high density of dislocation is formed. This occurs because the ultrafine grains have the maximum size required for the formation of intragranular dislocation structures, while grain boundaries play a significant role in dislocation annihilation during gigacycle tests. That is all for now, and we are working towards more improvement in future. Thank you all for attention and have a good day. Goodbye.